recording this so that it will be available a little later on YouTube for someone who might have missed it or interested in looking back at it or can't sit through it at the moment, or even to go back and see any of the resource slides that I've got listed here. So today we're going to be talking about the use of a ground fault locator to find a damaged cable that is buried. And this is a lot less common an issue than finding the path of a cable and some of the other kinds of simple electrical testing we've talked about, but it's a very useful thing, and those of you who have used it will recognize the time you've been able to save with test equipment. The whole idea with test equipment, of course, is that it saves you time and it makes you more efficient. So finding and troubleshooting things with electrical test equipment is a great time saver. So let's get on to talk about the ground fault location. Our objectives today are going to be to when to use an electronic fault locator. There are a lot of ways of finding faults that you don't necessarily need to have a sophisticated electronic tester to use, but you can use one to save time. We got to understand the principles of the thing, so it's always good to understand how something works. It helps you figure out unusual problems that come along or to do the troubleshooting a little faster. And we're going to understand when it works for you, the benefits, and the limitations that it might have as you are troubleshooting in the field. So the equipment that we have here today is that we're talking about is the ground fault locator, and we're using the Armada GFL 3000 as an example. This kind of pulsed technology, you may know under names like the A-frame, the pulsar, ground fault locator, is a technology pioneered originally by radio detection, and you may have also seen a device similar to this from Progressive Electronics or Armada and Greenlee. So if you have any of these devices, you can follow these very same techniques, really, because they all follow the same piece of technology generally. You need to have a locator as well, because the ground fault locator is not very much used if you don't know the path of the cable you're troubleshooting. So you always have had to have had the path of the cable located. This is critical to accuracy. When do you need to use a ground fault locator? When you think that you have a damaged cable and you don't know where that is, where the damage has occurred. And it seems obvious, well, I can't see where the damage has occurred, but sometimes you can use other techniques to try to figure out whether or not the cable, where the damage might have occurred. Anything like someone who's been planting trees, driving stakes, potholing, digging with a shovel. Those kinds of things can save you some time trying to chase them down with an electronic troubleshooter. To know when the cable has had some damage, you can use an electrical meter, very commonly use an electrical meter to determine if there is a low resistance to ground from the insulated cable. And the cables we're talking about here are insulated copper cables, typically, control wires for irrigation, power wires even for remote pumps, any number of insulated cables. And the problem that's occurred is that there is a compromise in the insulation that's caused a low resistance to ground. You can measure those with a meter and determine if that's really the case. You can also open, when you're doing this kind of testing, you lift both ends of the cable from any connections that are there. You can kind of short circuit one end of the cable and go to the other end and test it with a meter, and if it shows open, you've got an open cable somewhere in between. These are all just ways of verifying that it's worth the time and trouble to try to figure out if that's what's going on with you. Use the easiest way to find it that you can. That means using an AC clamp meter, means using your Mark I eyeball, or using a ground fault locator. All of these things can lead you to the trouble. Examples of the kind of damage that have occurred, and a number of you have probably seen these things. I know that I have. I had a cable TV locating guy come in and mark the cable TV drop by driving colored spikes into the ground. He drove a spike right through my irrigation wire and skinned it. I was able to find that by looking for his spike. It went right through the place where I know my cable was buried. Insulation chewed off by a rodent. Some parts of the country that's especially difficult because there's so many. Rodents like to tunnel along soft ground, and where you've buried pipes and wires is softer ground than around there. Especially true here in Arizona where I am, where the ground can be pretty hard, and gophers will want to follow the softest path. So, and as they go along a wire, for some reason they feel motivated to chew the insulation off. If it's a power cable, they get fried. If it's just a low voltage cable like the type we usually see, then it just remains damaged and maybe corroded. Cable cut by a shovel, such a common thing. People burying, putting trees in, and doing a number of things. You can see where these activities have gone on. So very often this is how you can find where the problem has occurred. But sometimes it's been very subtle, and it's difficult to locate. And that's when we get our tester out and start tracking things down. Over time, cables tend to be, they're buried, they're metal, they're plastic, and when they're direct buried, as time goes by, all kinds of compromises occur, including cracked plastic, and a little bit of moisture in an electrical cable is a difficult thing. What I'm showing here is our irrigation troubleshooting chart. The chart is used to do all kinds of, that's the whole process actually of troubleshooting, beginning at an irrigation controller, going all the way down to a diaphragm in the field. We use this to help illustrate the types of electrical equipment that are used for each of these parts of the troubleshooting, and as you can see there in yellow, I've kind of illustrated what we're talking about today. Once we've decided that there's a problem with the wire that's been compromised, we need to find out what's going on in between the controller and wherever the wire is doing its job downstream in a valve box or something. We need to locate the path and find it using an A-frame. Or visually, as I said, you can even do that kind of locating. So our goal here really with the GFL is to find a suspected ground fault. That's the whole thing, is we need to get out there and figure out where some damage has occurred or potentially occurred. Sometimes the damage is intermittent. It only appears when the ground is wet or that it's been watered, for example. When it's dry, it's not there. Very common problem with bad splices and nicks in insulation as opposed to completely cut wires. We are going to, when you're doing this, number one, you have to locate the path of the cable. So get your locator out, or maybe someone else has done it. Find out where the cable's running, and then begin to do the wire pulsing with the GFL. And we'll show in a second just how that goes on and how that works. It's important to kind of understand that underlying technology. So the ground pulse that we're providing here, this is an insulated cable normally, of course, which is what we're dealing with. If the insulation has been compromised, then it's open to the earth, and you put a high voltage pulse on it, and it causes a ripple, like a ripple in a pond, like a stone being dropped into water. And these ripples return to the ground stake, and we detect them by using the A-frame, which has two probes on it. It can tell what direction the ripples are passing from and going toward. This is the whole concept behind the use of the ground fault locator, which is why the A-frame is kind of a big unwieldy thing. It's like got two probes that are about 3 feet apart with a meter that mounts in the middle. The way this works, in the case of GFL 3000, you can select between a couple of different voltage levels, but the lowest is, believe it or not, the lowest is 2400 volts. Because it's a fairly small damage point potentially on the cable, a small skin in the insulation or something, we use a pretty high voltage, and it creates this nice sweeping path through the earth that goes back to the ground rod where the A-frame pulsar unit is located. It spreads out in a way that lets us tell what direction we are relative to where the thing has occurred. There's a higher voltage setting on the locator that you can use, but it finds the smaller damage. I always recommend we start out with the smallest pulse, which is 2400 volts, and it should find only the larger damage. When you get into chasing down damage on a cable, you can often find that there are multiple places where damage has occurred. It just hasn't become a problem yet, and you're looking for the main one. You might find that a cable has been cut, but somewhere in between where you're starting out and where the cable has been cut, you have a couple places where some damage has been. So be prepared for seeing multiple locations or faults. So the faults are unknown, and that's what we're after here. I should mention that because that's a 2400 volt pulse, at least, that's coming out of the unit, you want to be careful with handling this. Once you've got the thing set up, you connect it like a locator, and locator puts out a high voltage too, but not this high. You connect it like a locator, and you start doing your work out in the field, looking for the place where the ripples are occurring in the ground, and tracking down that unknown location of a fault. When you get there, you need to remember that when you've decided that you're on location, go back and shut off the transmitter. The transmitter beeps whenever it transmits its voltage. It's kind of a handy reminder. About every 3 seconds it pulses and gives a beep. But you can get out of range where you don't hear that anymore. You don't hear it over traffic noise. You forget that thing's going on. You find the problem, you start digging, you get down there and start handling the wire, and it will wake you up. It's not going to start a fire or kill anyone, but if you get down there and touch that wire that's got a couple thousand volts on it, you will remember it. It's kind of like what I call my cholla cactus story. You only touch one once, and then you remember it forever after that. So back to this issue of knowing the path, you have to have the path, because as we are searching for faults, we begin by going along the cable run. We're going laterally down the cable until we find a place where the ripples in the ground reverse and we're over the top of the fault. Then secondly, we go across the run with our A-frame to make sure that the fault is directly crossways on the cable using the same kind of meter indications. When we've done this, I often tell people what we've done is found the fault within one shovel width. By the time you've done the location along the run and across the run, you are able to just take a hand shovel and probably go right down to the place you're looking. Very good, very useful technique. I throw in this little application tip because a lot of situations out there, different kinds of cables that are split in runs, common runs in irrigation systems that go different directions. As you get out there and you start to do as you'll see in our demonstration, we do a little demonstration on a very straight piece of wire, which is great. It helps illustrate the concepts. But in real life, you sometimes find that cables that you're tracking are going back and forth and serpentining and splitting and that kind of thing. So you have to watch out for the effects of that. Generally, when you are walking, you've mapped this cable out. As you walk along and you're putting the A-frame down every 30 to 100 feet, depending on how far you're going, you will get these kicks. But sometimes the kicks seem a little nonsensical. It's like it does things that might even give you a false indication of a reversal because the cable is crisscrossing where the ground ripples are occurring. You can double check for false indications like that by doing the cross check across the run. The same thing that gives us the really tight indication about the location of the fault. If you cannot do a triangulation on the fault across the cable, you are in a false location and you need to keep going. Generally, the rule of thumb is when you are getting goofy indications, you're not sure, it seems to be pinging in the wrong direction or the signal has gone away, you just need to keep going. So always keep going. When you get close to the place where the fault has occurred, you'll start getting indications that make a whole lot more sense and you realize you're on top of the good thing. And then you do your cross check across the wire and compare it with your lateral and you'll get a good find. Just keep going. What I'm going to do, even though this is illustrations of a nice straight piece of cable, it does show something about how we I'm going to have to switch over to the video here, how the thing looks and how it gets used and what you hear sound-wise. So I am going to switch over. If you give me just a moment, we will switch applications. I have to change the audio, and we'll go to the video in just a moment.
We will demonstrate this process using the Armada Technologies GFL 3000 Ground Fault Locator. The GFL 3000 is designed to pinpoint the exact location of a ground fault in a cable. The GFL 3000 is not intended to locate the entire path of a cable. To effectively pinpoint the location of a fault using the GFL 3000, the path of the cable must be previously determined and the wire must be in direct contact with the earth. To demonstrate that the path of the wire has been previously determined, the wire has been placed above ground. The fault is illustrated with a flag for further clarity. In cases where the wire is contained in conduit, the conduit will interfere with the locator signal and not result in an accurate reading. Isolate the cable to be tested by disconnecting it at both ends. Make sure the cable is disconnected from power, components, or anything else that could transmit an electrical current. This forces the current generated by the transmitter to exit the cable at the fault. At either end of the cable, and with the transmitter off, connect the black lead to the ground stake and push the stake into the ground as deeply as possible. Connect the red lead to the cable that is being tested. Note that if the clock is indoors, the black lead must be connected to its own ground stake where the wires exit the building. Do not use existing grounds in the building. Before turning on the transmitter, be sure no one is touching the stake, cable, or leads. When turned on, the transmitter will produce a beeping sound indicating current is being transmitted. Select low or high power as per your preference. High power will find all leaks, large or small. Low power will concentrate on larger faults. Remove the black insulating covers on the probes of the receiver. Turn the receiver on and place the receiver probes into the ground along the path of the cable. As the transmitter pulses the current, you should see the needle on the receiver kick in the direction of the fault. Watch for the direction of the initial kick of the needle and disregard the rebound kick. Remove the A-frame probes from the ground and move it in the direction of the initial needle kick along the path of the cable. Reinsert the probes into the ground and observe the direction of the initial needle kick. Continue down the path of the cable in this manner until the needle kicks in the opposite direction. This indicates a fault is between the last two places the receiver probes were inserted. Continue to zero in on the fault by following the initial needle kicks. When you are directly over the fault, the needle will cease to kick. Mark this spot for repair. Before repair, turn off the transmitter and disconnect it from the cable. Never touch the transmitter, leads, or the cable being tested while the transmitter is on, and do not use the transmitter in the rain. Failure to follow these precautions could lead to injury or death. Cables that contain many faults can be confusing as all the faults exhibit some needle kick. To minimize confusion, start near the transmitter and work your way along the cable, fixing the faults as you locate them. If you are next to the transmitter when using the receiver, the needle can kick in the direction of the transmitter. Move further down the cable, away from the transmitter to get the proper direction of kick. It is not uncommon for needle kicks to cease between the transmitter and the fault. As you move away from the transmitter, the needle response should decrease and could eventually stop. The needle will begin to kick again as it nears the fault. Small faults may be indicated by weaker kicks. To focus on larger faults, turn the transmitter power to the low setting. If you are unable to insert the probes into the ground due to concrete or asphalt, wet sponges between the ground and each probe can increase the conductivity of the frame. To bridge large obstacles, you can extend the frame by wrapping one end of wire around 1 foot of the A-frame and the other end around the screwdriver. Then use the screwdriver as you would the second probe.
Alrighty. Hopefully you're able to hear that all right. It's really good to be able to see the unit in use. It's best always, of course, to actually use the unit or have it demonstrated by handling it. But the video is the next best thing, much better than slides, of course. So one of the things that he didn't do in the video there is to show you the crossways checking of the fault location. Once you go past the location and the needle's kicking in the other way, then you find the 0 point where the needle is not kicking at all when it beeps. And then you turn it crossways at 90 degrees to the path of the cable and make sure that you have a null in that direction also. That's how you're going to get the real shovel width location of the fault, something to work with. So I should mention that. Some of the tips on there were actually pretty good and interesting. I'm going to reiterate some of those. But finding multiple faults along the cable. When in doubt, keep going. If you're going along and you find a fault, you could fix that fault and look for another one, because when people are going out looking for main faults, cuts even, you will find some smaller faults along the way. So you need to kind of fix them and clean them up as you go. So keep going and move along. Bends in the cable can cause some readings that don't seem to make very much sense. You just need to keep going along the path and see if you recover the normal kicks, because as the cable serpentines, as it disappears, as it crosses another obstacle, you may find some funny readings. But if you keep following the path, as you approach the problem, you will see the kicks and get the reversal you're looking for. So keep going is the watchword here. You may lose the signal along the cable, in which case you need to keep going. The fault, even if we're getting a good kick out of a fault, the ripples may not be strong enough if the fault is way down the cable. Remember that these ripples are spreading out into the earth and kind of dissipating and spreading across the earth and rejoining at the ground stake. And when that's happening, they're pretty weak where they've spread out the most. But as you approach the fault, you'll pick up the signal again. There's some good tricks about testing on paved areas. Involve either putting wet sponges on the tips of the probe, There's quite a bit of moisture in things like concrete, for example. If you put wet sponges on the tips, you can actually continue to do your fault locating under concrete. Some of that's true of pavement as well, but you can also do a trick with extending the A-frame across the road with a wire and a second probe like a screwdriver. Different technique that I won't go into great detail here. I have heard some issues that have raised recently. People with 2-wire irrigation systems that have lightning protection may have a buried copper wire next to the main cable, uninsulated. That'll do is tend to mess up the whole ripple situation because the copper wire will absorb the ripples. You may run into that if you're in a 2-wire system or a system that has your lightning protection. You might watch out for that if you're getting very difficult readings. There's no handy way around that, I'm afraid, that I'm aware of. Next Friday, we're going to be doing the Find It, Fix It on modern wire and valve locators. There are features that have appeared in locators in the last 10 years that are not in all the ones that people have used forever. If you use an old Greenleaf 521 or Progressive 521 for a while, it doesn't have features that current locators do, and they're constantly being upgraded, and I'm including in that connectionless tracing, antenna switching in the receiver, improved sensitivity, resistance to noise. We're going to cover that, and that'll be next Friday. And all these schedules for our webinars are available on our blog, which is armadaupdate.wordpress.com, as you can see here. What we also do, because these videos are really useful, we have over 20 videos on YouTube, is we publish a little application note that has some QR codes on it. And those QR codes can be scanned by your smartphone. For example, there, the top left one is the Pro 800D locator instructions. That's a 10 or 12 minute video, longer than I usually can sit through, but it covers it pretty completely. If you're not using one frequently, it touches on everything you do. Scan that QR code with your smartphone, takes you to the YouTube site and plays the video for you. Handy thing for infrequent users and renters, that kind of thing. The one that we just did, that video you just saw on the GFL, is also on there. It's also on there in Spanish. So if you want to see it in Spanish, the QR code in the lower right is the GFL 3000 Espanol, and you can scan that and see that overdubbed in Spanish. Other resources available, our main site is the armadatech.com, and YouTube site is, the channel name is Armadatech. So it's youtube.com/user/Armadatech, although you can go to there, just go to their homepage and search for Armadatech. We're on Facebook, partly as a way to make it easier to find the other sites we have. If you go there, you can find links that take you to the main site and take you to the blog site, for example. We also try to cover the schedule for webinars at the Facebook site. So the Armada blog, again, is armadaupdate.wordpress.com. Application notes and schedules and things like that, PDFs that you can download. And I am Jim Carefoot, and I am available via jcarefoot@armadatech.com. Feel free to send me an email with any questions, any comments, topics you'd like to see covered on our Friday webinars. And with that, we are keeping it under 30 minutes. And I appreciate your showing up today, and we will hope to see you at the next one. Bye.